So yesterday, we did have the complete proof of the Kahn-Kalai conjecture. We'll see lots of variants of it today, and the main thing you need to remember from yesterday would just be the proof of the key lemma, relying on the minimum fragment. So we'll see that today we can just take kind of exactly the same thing that we did yesterday, and it will very easily, in a streamlined way, give us quite a few corollaries in different contexts. So we'll see how powerful a simple idea can be. But first, maybe because there was also a question about this, let me quickly mention. So this is one general way that we can obtain upper bound on the expectation threshold. Okay, and this is, of course, useful in applications, right? Because if we want to use, for example, the Kahn-Kalai conjecture, which tells us that the truth threshold, which we care about, is upper bounded by, well, some quantity times the expectation threshold. And in particular, then we will care about how we can put reasonable upper bounds on how we can estimate this expectation threshold in general. So this procedure is, again, going back to an observation in a paper of Talagrand. So I will first write the expectation threshold this way. So this is just recalling the definition of it. So as you remember, it would be the largest P for which the family H is P small. So if we re-express that, what does that mean? The family H is P small if it has a cover G that has the P cost less than 1/2. So let me write it this way. So I will optimize over all covers G of H. So G is a cover for H if it satisfies these constraints. Let me write it this way. So the sum over, or actually, let me write it in a more suggestive form. So let me write G as a function that maps the subsets of X to the value either 0 or 1. So of course, this is the same as the collection of subsets of X. And we want the constraint that whenever we look at a set H from our family strip H, then the sum over G subset of H of the indicator that G belongs to this cover strip G have to be at least 1. Okay, so this is saying nothing but the statement that for every H in H, there exists at least one set from G, which is a subset of H. That's the same as our definition for cover. And then the cost of the cover is just the sum over every set in the cover, P raised to the size of that set, right? And then we say that H is P small if there exists a cover with cost less than 1/2. So that's just the same as saying that this minimization problem would give us an output that is less than 1/2. So this is just to rephrase in a different notation, the definition of the expectation threshold. And so quite clearly, we can see here that I intentionally write down in this notation. So to suggest that this is just a usual linear integer programming problem. Right, so we have here just linear constraints in terms of the variables that are G of G for over subsets G of X. And here we have an optimized value that is also linear in terms of these variables G of G. And we have the constraint that the variables have to take values either 0 or 1. So this is a standard integer linear program. So once we write it in this form, well, one very sensible way of upper bounding this quantity would be just to relax these constraints here from being either 0 or 1 to taking values inside the interval 0, 1. So a very standard relaxation in linear programming. So let me write it this way. So because now I allow fractional values, let me change the notation from G to W. So now W is a weight function that assigns some non-negative weight to every subset of X. And then we have exactly the same objective function as before. So here this is summing over all subsets G of X. And the constraints are that the sum over G subsets of H, W of G, have to be at least 1 for all H from alpha discrete H. And again, we want this linear program now to satisfy that the optimal value is at most 1/2. And the largest value of P for which this holds will certainly be at least the largest value of P for which this holds, because every solution that you can plug in here will also automatically be a feasible solution here. Okay. So now, because I have written it in this linear programming form, well, a natural step for us to do is to take the dual of this linear program right here. Right? So we can then rewrite this as, so let's keep this part outside the same, and we'll just rewrite this program in terms of its dual. So for the dual, we'll have one variable for each of the constraints here. So we will have this maximization problem, and the variables are going to be values lambda that assigns non-negative values to the sets in H. And if you check what the dual should be, then you will get here exactly this objective function and these constraints. And again, this to be at low. Okay, so between this and this, nothing happens, just linear programming duality. And so in particular, one variable for each constraint here, and here we have one constraint for each variable in the original problem. So now here the variables are on the subsets G of X. So now we have one constraint for each G. And well, you can do this, but this is exactly what the dual problem should be. Okay, so I can do a little bit more simplification here that will be useful for us later. So I can now rewrite this in the following language. Okay, so in the last step, I just do one small rephrasing of this. So this is now the largest P for which this maximization problem returns a value at most 1/2. I can also rephrase it as it will be equal to the smallest P for which this maximization problem returns to us an answer that is at least 1/2. Right. So it is the infimum P for which there exists lambda from the family H, say 2, 0, 1. The sum over H, lambda of H, is equal to 1/2, and the constraints over there is satisfied. Okay. And just because this 1/2 is a little bit annoying for the normalization, I will actually just rewrite this in a slightly, just renormalize it to make it more convenient for us elsewhere. And I'll just put the 2 here. Okay, so now let's reinterpret this quantity here. What are we saying? This is whatever, the smallest P for which there exists a probability measure lambda This is a probability measure on the sets in our family strip H. And this probability measure has this nice property that no matter which set G, a subset of X that you choose, the total amount of the measure on the sets H sitting on top of this specific spot will have to be small and will have to decay roughly like P to the size of the spot that you have fixed. Okay, so I will take this as a definition. So we'll say that
if you scale, you need to replace that 0, 0, 1 interval to 0, 2 interval.
Yes. So in the end, the interval is not going to be so important. Maybe so you can put here, maybe you only constrain that the values of lambda is at least 0, and you can put here the same. But anyway, because they sum to 1, all of the lambdas will be between 0 and 1. So for that one, it's not very important. So here, let me say or define that lambda is p spread. Right? So lambda is a probability measure on H if this condition holds. Okay. And just because it will also be useful for us somewhere else, let me say any W, so kind of a weight assignments assigned to the subset of X with this constraint, we'll say that W is a fractional cover. For H, right? So we're just taking exactly the same constraints that we want for the usual notion of the cover, and we allow the variables to receive fractional values. So we'll just call this a fractional cover of H. Okay, so with that, let me define what people would call the fractional expectation threshold. So the fractional expectation threshold yes, this will be exactly the output here. Okay, so this is the smallest p such that there exists a p spread measure lambda on H, or if you prefer, is the largest p such that there exists a fractional cover W of H with this cost. So W of G, e to the G is a subset of X at mod 1. And by this relaxation step and duality, we saw that PE is always up about it by PF. But at the same time, what is useful about PF is exactly this definition, right? So in particular, we will be able to put an upper bound on PF and hence PE as long as we can construct a p spread measure on H. Okay, so so we will see from tomorrow when we start to go into the combinatorial application that there usually our task will be to construct these p spread measures for a given family of combinatorial structure, and we'll see how extremal combinatorics is useful for that later. So for now, with that setup, let me get to the next connection that I want to tell you. So I will next tell you connections to the system and sunflower, which was actually of the original developments that led to many of the things that we discussed and where there are lots of crucial insights going back to the sunflower breakthrough. So first, That is a sunflower. So a sunflower, an R sunflower, is a collection of sets A1 up to AR, or with the condition that every pairwise intersection, AI intersected with AJ, is actually equal to the common intersection for all I different functions. Okay, so in picture, a sunflower would look like this, where you have a bunch of sets. And apart from the common intersection, the rest of the sets have to be disjoint. Okay, so this is for example, a picture of a four sunflower. Okay, and really the motivating question here was old conjecture that for every collection of, well, some constant, potentially depending on R, raised to the L sets. So if you are given any exponential in L, number of sets of size L, then there should be an R sunflower consisting of distinct sets. Okay.
Yes, if that second line max is greater equal or smaller.
That is still smaller than or equal to 1. Yes, so well, just maybe the final remark I will make here is just a very quick comment that I'll say H is P spread. If there exists a measure lambda, that's P spread on it. So if PF of H is at most P by definition, and you can observe just by what we state here, that being P spread is a stronger condition. So it implies that H is not P small. This is just a rephrase of this inequality here, but we'll use it a bit later. So I just mention it. So being P spread is a stronger condition than being not P small. Okay. So, all right. So I mentioned over there the sunflower conjecture. This is still open, but the sunflower breakthrough around 2019 made significant progress towards the sunflower towards the conjecture over there. I'll state that result shortly. Let me first mention why these sunflowers have anything to do with being not P small or being P spread. So the type of conditions that we have been discussing. Okay. So let me consider the following argument. So let H be an arbitrary family of C to the L many L sets. Okay. And C doesn't have to be a constant here. So it can be super constant. It can be an appropriate function of L. You'll see that it mostly doesn't matter. So let me just first set up this argument in this. Okay. When you have C to the L many sets of size L. Now, if lambda, which is the uniform distribution on H, if this is not the 1 over C spread, constant here. No, wait, this is fine. So 1 over C spread. So a priori, we start with an arbitrary family of sets. There's nothing like a smallness or a spreadness property associated to this family of sets. Okay, but towards at least the sunflower conjecture, let's make this for the following observation. So if H is not spread, in particular, not 1 over C small, yet we can do the following operation. Well, being not 1 over C spread means in particular that there exists some subset G of the ground set such that the number of sets from the family strip H that contains this set G is at least 2 times 1 over C to the size of G times the total number of sets in H. This is by definition of the spread measure or failure of the spread property. So in particular, we can now replace the family H by this family of sets. So we consider all of the sets of the form H minus G, where H was from our original family and it contains G. Okay. Now this is going to be a collection of, well, even more than C to the L minus G sets. Okay, so if you could have proved the sunflower conjecture with this smaller parameter L minus G, so if you could prove that whenever you have C to the L minus G many L minus G sets, there is a desired sunflower, then you would be done. Okay, and you can easily see that you can put back the set G and you have produced a sunflower in the original family of sets H. So in particular, this will tell us that if we want to prove the sunflower conjecture, then we can just assume for free that the family H has this 1 over C spread property. So we just write that conclusion. So for the conjecture, we can assume that H is 1 over C squared. And furthermore, this doesn't hold, as I already remarked, just it doesn't only hold for constant C. Even if C is a function of L, like log L, log L, log L, something like that, then this same argument would go through. And if you want to prove the weakening of the sunflower conjecture, then you can do that under this additional assumption that the family H is the corresponding 1 over C squared. Okay, so with that, let me now state this is a key step in the amazing sunflower breakthrough of Alwise, Lovett, Wu, and Zhang. So what they prove is that if you have, well, the exact result they prove is roughly that if you have a family of sets H, that is 1 over log L, log L spread. Well, H, let's assume that it is uniform, L uniform. So every set in H has size L. Then if you take a random subset of the domain with some appropriate small constant probability, this random subset of the domain with a small constant probability will contain at least one set from H with probability 1. Okay, so I'll remark to you in a little bit why, as a corollary of this, you will be able to deduce that any collection of C, maybe C depending on R, log L, log L, L sets to the L sets would have to contain NR sunflower. But because we'll see a sharper bound in just a second. Now I'll tell you about this deduction in a little bit. Okay, but already this version of the lemma of the theorem, which is now one of the earliest form of what we call the spread lemma, already appears in this beautiful sunflower breakthrough of Alwai, Slovett, Wu, and Zhang. And it contains the very beautiful, many of the beautiful ideas that are crucial to the later works in this area. So in particular now, let me tell you about what you can do after you, okay, so let's piece some of the things together. So Talagrand already kind of tell us the relation between this word of spreadness, which also somehow comes up naturally when you work on sunflowers, and the study of threshold, right? Via exactly this discussion right here. And if you realize that connection, then one can actually take the beautiful sunflower argument here and then introduce some further refinement, and one would get the following result, which you can now think of as the official version of the spread lemma, or you can think about it as the fractional Kahn-Kalai conjecture. So this is the result of Princeton and Diana Park. Also in 2019. So in particular, this resolve a conjecture of Talagrand. This is a weakening of the Kahn-Kalai conjecture, the fractional Kahn-Kalai conjecture. So they show here that if H is P-spread, then an L uniform you sample a random subset of X with density Cp log L. Okay. Then it will contain at least one set of H with probability at least from that. Okay. So this is a refinement of the lemma of Alwai, Slovett, Wu, and Zhang. And here for the sunflower application, they actually only care about really the range where P is fairly large, almost constant. So they only work in that range of parameter. But if this result, by refining the proof, would allow you to also get the result to work even for much smaller P, which is relevant for applications to threshold. So you do ALWC argument. One can obtain this. And at this point, as I already mentioned before, if H is P-spread, then H is not P-small. So in particular, this is going to be the corollary of the Kahn-Kalai conjecture. But actually, instead of just saying that you can use the output, the Kahn-Kalai conjecture, to reobtain this statement, we can actually look into the proof that we had for the Kahn-Kalai conjecture under this stronger assumption, and let's see what is kind of a stronger property that it gives. And how we're going to do this, because we will again do this for a few other applications. So hopefully this is useful. So under this P-spread setup, we can strengthen the key lemma to the following even more convenient form. So we can prove this new version of the key lemma, where if H is P-spread, L bounded. So every set in H has size equals L. Then with probability at least 1/2 over a subset W drawn according to this distribution XCP, you can show that all but an epsilon fraction of sets in H need to have the property that the corresponding fragment, remember, so T of WH is small, decays by a factor of 2. So this is kind of an even more convenient form of the key lemma that we saw in the setting of H being not P small. So if you remember for the definition, for every W and every H, we define this minimum fragment, T of WH. And that's kind of the smallest subset of H for which we can add to W and obtain some set that contains some other set in the family script H. And in the P-spread setting, it turns out that the proof of the key lemma would allow us to guarantee this stronger property that if we just sample a random subset of X with density C times P, then most H from our family script H is actually, with high probability, forced to produce a small fragment with this random set W. Okay, so in particular, if you want to prove from this version of the key lemma, the spread lemma right here, then the argument is even more convenient than the iteration that we had to do yesterday, right? Because most of the sets in H would produce a small fragment. Let's just define the new collection, H1, to be the collection of all of these small fragments. And we forget about the rest of the sets in H. This will still inherit the spread property from the original family H because it contains almost every set from the original family lives on to produce a small subset in this family H1. So you can just now iterate this argument and directly observe that by the end of the argument, the size of the sets in this family HI will have to shrink to 0, but still we need to have a lot of them remaining in our collection. So we will necessarily produce lots of empty sets in the final collection. And if you remember what that means that the union of the random samples we take along the way will contain some set from the family script H. Anyway, so the iteration will be very simple once you have this type of guarantee right here. So let's just see quickly how we can prove this version of the key lemma.
Can you put that board up?
Oh, yes. Okay, so let's give maybe just a quick sketch of proof of this other version of the key lemma. Okay, so if I look at it in this way, well, what do I want to do? Let me bound the expected value when X is sampled, when W is sampled according to XCP of the number of sets in H that produces a large fragment with W. So I'm trying to count the number of sets in H for which this fragment T that W produces with H is very large. Well, if you remember how we do this, well, let's think about this argument this way. Well, I want to use the key property of the minimum fragment from yesterday's lecture. So let me do the count in the following form. So first, I will count over pairs WT, where the size of T is large, and T is a fragment of W with some H. And then I will sum. Okay, and then in here, I will have PCP of W, the probability that we sample the set W, together with the count of sets from the family script H that contains this fragment T. Okay, so at least this is, we can easily see to be an upper bound on the quantity that we care about. But because we have the key property, let's change the variable in the exact same way that we did yesterday. So instead of counting through W and T, we are going to count through Z. Okay. So we are going to sum over Z. And if you want, you can put the constraint that it is a feasible set. So Z belongs to the family H. Inside, we would have, okay, so this is some of the same manipulations that we did yesterday. So let me be a tiny bit fast. So we have, when we change the measure between W and Z, we incur this factor of 1 minus CP to the T to the, so let me write this way, to the T over CP to the T, sum over T larger than L over 2. Okay, and in the remaining piece here, I will have the sum over subsets T of H hat Z, the same key property with size exactly T. And here B again, you can put the number of H that contains T. Okay, so this change of variable is going to happen a lot today. So it's always what we do. We always just swap the way that we count from this W and T. So we can see that, yeah, so once we count W and T, counting H will not be so hard given the spread condition. I'll do that step right now. But the T non-trivial change is always between the count from the pair WT to the count from Z. Okay, which is what we just did here. So now let's add in the spread condition. So we have here the sum over large T, sum over Z. Let's remove the small factor. So let's just keep track of 1 over CP to the T. And because our family H is spread, the number of sets H sitting on top of a set T is at most 2P to the T times the total size of H. Okay, so this we use the P spread property. H is P spread. So one thing that I didn't fully remark, when we have a family of sets H that is P spread under some general measure lambda, you can imagine that you make H some multi-set, some multi-subset of some multi-family of subsets of X. And you can always just assume without loss of generality that you are handling the uniform measure on the set system script H, which is what we are doing here. And given that, we will have this bound for that count over there. And then the only thing left that we didn't count is the number of ways to choose T as a subset of H hat of size little t. That is going to be L choose T. Okay, so now exactly the same calculation as we did yesterday will tell us that this is at most some small factor, maybe 4 times 4 over C to the L over 2 times the size of H.
Here we can do L choose T because for every Z we already designate the H hat, right?
Yeah,
Okay.
that's the point, right? So Z is very large. So choosing T from Z would be an absolutely enormous cost. But from every Z, we already designate for free this fixed set H hat, which only has size L. That is what helps us to L choose T. Okay, so that proves this version of the key lemma is mostly similar to what we did yesterday. I just want to bring it up because we will then see it again in a different context. Okay, so with that, let me now state what do we know best now on sunflower. So let me say that this is an output of a sequence of many words. So starting from the sunflower breakthrough, and then the fractional Kahn-Kalai conjecture. There's also work of Rao, and then Bell, Lucha, and one cube. So what we do know now is that any family of some absolute constant times R times log L to the L set would have to contain a sunflower. Okay, so at this point, let me tell you the quick deduction so we are all on the same page. So how are we going to deduce this? Oh. Here. The spread lemma, it is not so hard to see this. So as we saw before already, we observed that we can assume the family H that where we want to find a sunflower in is spread, where the spread parameter is going to be 1 over this. Okay. So in particular, it is not, if you want even weaker condition, it is not 1 over CR log F small. So what we saw is that if we sample a random subset of X, where each element is chosen independently with probability. Okay, so let me write this way. So if we sample a subset of X, where the density that we sample is some other constant over C R. Yes. Okay, so we know that if we blow up this probability by a factor of log L, then we already can guarantee that we will contain at least one of the sets from H with reasonably high probability. In fact, even with high probability, if you assume L is large. Okay, so in particular, we have this set X with density C prime over CR. And we can guarantee that these sets will be lying in H with reasonable probability. So what you can observe is that you can take a uniformly random partition of X to, let's say, 2R parts. Okay. And it's not so hard to compare the distribution of each part in this uniformly random partition to this random subset of X with density 1 over 2R. Okay, so if you now choose this constant C correctly, then you can guarantee that each part will contain at least one set from H with probability at least 1. Okay, so, well, at this point, the expected number of parts, so we have our domain X, we take a random partition of X into a number of parts, 2R parts to be exact. each part will contain a set from H with probability at least 1/2. So in expectation, at least R parts will contain a set from H. So there will be some realization of this random partition where you can find R parts that contains a set from H. But this is a random partition, so these sets are automatically disjoint. So this just produced to you an R sunflower. Okay. So kind of the procedure. And you can see this procedure is useful for producing collections of disjoint sets. So there are also some further applications in very nice applications in intersecting set systems by Kupowski and Zakharov. But I will not get to the details of these. Okay, so yeah, with this streamline proof, you can actually uncover a very reasonable constant, and you can be careful on optimize constant. I believe should be the best constant that we know that guarantee a sunflower. Any question?
Please consider the LS and LL is conjecture rather than the LS and Laos of the conjecture. Then do you think still the his bad measure can work for everything?
Right, that. Yeah, so far that turns out to be a fairly different setup. Yeah, we can maybe talk about that more later. Yeah. Okay, so right, there are two more things around this topic that I want to say, but perhaps, okay, I'll say one useful observation, very useful observation for us, okay, especially in the later part of this course. So there were some questions about the cases in which we can remove the log factor. And at least in combinatorial applications, one of the very useful cases or conditions that guarantee this is this notion of a smooth spread property was defined by spiral. So here we say that a hypergraph H, let's say associated with a measure, probability measure lambda on H, is P, and then you have some parameter, R1, R2, let's say up to RK, spread. If the following property holds, so R1 should be kind of the uniformity of H, so H is R1 bounded. And Rk is equal to 1. Our i's are going to be a decreasing sequence of number. And the most important condition is that for all sets A of size between Ri plus 1, Ri, you have the following condition. The measure lambda of the sets in the family H that sits on top of A and wait, okay, so no, not this for a second. The number of sets from the family H for which H intersect with A is equal to T. This is at most, let's ignore the T, so P to the T. So this is for all T, at least I plus 1. Okay. Okay, so roughly before in the spread condition, what we control is the number of sets H that sits on top of a specific set A. And actually, if you look carefully at the condition, you can actually think about it as for every set H, you may fix some specific spot A inside a set H. And then what you care about is how many other sets H prime can intersect H in this specific spot A. A spread condition would allow you to exactly control the fraction of set H prime sitting on top of this specific subset A. But in that case, if you want to, for example, sum over all H prime that intersect H in a reasonably large subset, you would then have to do the union bound or the sum over the subsets A of H satisfying certain size conditions. And that would incur some additional combinatorial factor beyond this P to the T. And these are kind of responsible for the log factor if you're only assuming the usual spread condition. But here, what is different in this condition is that we are not actually, so once we are given this set A, okay, let me not use that as A, let me use that as B, and think about this as A. So B has size T, right? And so if you want to control the number of sets H that intersect A in a set of size T, usually you would have to sum over all subsets B of A of size T, and then you can apply the spread bound, which is P to the T. But here we are assuming a stronger condition that the number of sets H intersecting A in size T will be bounded already by the bound that we have from the spread condition. So somehow we are assuming that we have a stronger property that allows us to remove this combinatorial sum over subsets B of A of size T. Okay, so why did we write down this condition? Maybe let me just put a small claim here and maybe do not do the full calculation. But the claim is that for a lot of the combinatorial structures, so for example, the Tth power of a Hamiltonian cycle so this is a graph. This is kind of the Hamiltonian cycle that you usually know. Imagine that you number them 1, 2, 3, 4, 5, and so on. And you are going to add also edges between every pair of vertices that are at distance at most t on the cycle. Okay, so that's the definition for the Tth power of a Hamiltonian cycle. And it turns out that you can check that the family of Tth power of the Hamiltonian cycle has the, well, P is going to be the expectation threshold. So that will be n to the minus t. Not that, 1 over t. And then you have these parameters Ri. The top one is going to be just the uniformity, so something like Tn, that's the number of edges you have here. And then they will decay by a power of n in every step. So this will hold true for some gamma, maybe depending on t. Okay, so you see that in finitely many iterations over these parameters Ri, you will drop down to 1. Okay. So, well, I stated, I told you that the spread property would allow you to remove the log factor. Let's really see how that works. So this is the result of spiral. And also independently as Puni Diaz person. And this also kind of already the original observation for this is actually from the paper of Kahn-Kalai and Park, where they show that for the second power of the Hamiltonian cycle, you don't need the additional log factor. And they can refine and generalize that. And okay, so the theorem is that this H is P R1 RK spread. Then a random subset of X with density C, P, K will contain a set from H with probability least 1. So let me give you this good sketch of the streamline proof that you can do if you follow the version of the key lemma we have proved. So again, let me stick to, so H may come with some general spread measure, but we can stick to the case where we're just working with the uniform measure on H. So again, let me try to bound the following quantity. So in the first step, when from R1, we will try to show that when we start from this R1 uniform hypergraph H, once we sample a random set W, all of the fragments will have size at most R2. And then we replace the family H by this R2 uniform collection of fragments. And then we just repeat the argument once more time to show that all of the next fragments will have to have size at most R3. Okay, so we just keep doing this until we have size RK, which is just 1, and then the last iteration finishes. So let's just actually see how it works in the first step, and then all of the other steps are of course similar. So let's sample a random subset W of X with density C times P. And let's count the number of H for which the fragment have size larger than R2. Okay. So we are going to do just the same things over again. Well, this is at most the sum. Okay, so maybe I will do it one step quicker. I will not go through the step where we count. Maybe let me still go through the step where we write out the pair W and T. T is a fragment. T of size at least R2. Okay, we have probability of W. And then we have the number of H that contains T. Okay, I can now do the change of variable. So we up about it by the sum over Z. And we have the probability of Z. Let's remove some of the small factor already. So the main factor we need to remember is 1 over Cp to the T. Let's put out here the sum over T at least R2. Okay, and now inside we are going to have, well, what exactly? So we'll have the sum over T subset of H hat of Z of size equal to T. And we will also sum over H containing T. Let's say, or just sum 1 here. Okay, so you can rewrite it a bit differently. So this is at most the sum over large T the sum over Z. So nothing happening. We have this Cp to the minus T. And then let me rewrite this last term in a way that is suggestive of the condition. So let me rewrite the last term as the number up about it by the number of sets H from the family string H, for which H intersected with H hat of Z have size at least T. Okay. So, well, the condition is stated for exactly T, but you can sum over T there if you wish. Okay, so you can now rewrite this bound as maybe the sum over t larger than R2. There's a standard sum over Z. There's Cp to the minus t. And then if you change here equal to t to at least t, you sum all of the p to the t. So maybe let's upper bound that just by 2p to the t times the size of the original family H. Okay, so at this point, you are done as usual, right? So this sum is at most 1. This sum would give you something that decays exponentially in L. So it's going to be smaller than some 1 over some big constant to the L times the size of it. Okay, so all in all, you have shown that in expected value, the number of sets H that produce a fragment of size bigger than R2 have to be in expected value at least a little old fraction, a small fraction of the entire collection H. So now just pick up all of the fragments that have size at most R2 and repeat this argument. And that's the case that we will be done.
So it's important here, we don't have this R1 choose T factor, right?
That's right. So what the condition does is to exactly remove that R1 choose T factor. So we move to the last application on this end that I will tell you about. So, well, the sunflower conjecture. So it's still there. Well, the bound that we have for the sunflower conjecture is still not a constant to the L, something like log L to the L. And there's one family that some people are interested in. So there's one question, which is if you have a collection H of L sets with some large number of sets, okay, and also with the condition that the VC dimension of this family is bounded, then can we improve the bound for the sunflower conjecture? And one of the motivating observations for this is that, well, if the sunflower conjecture is false, then whatever example witnessing that it is false, you can actually use it to then construct a counterexample to the sunflower conjecture that has bounded VC dimension. Okay, so maybe good first to figure out if the sunflower conjecture holds over set systems with bounded VC dimension. And Fox, Park, and Sook, they got a bound that is very close to, again, a constant to the L, but that constant looks like some exponential of log star L from a combinatorial argument. And for us now, I'll just state that actually, just again, tracing the proof that we have done here, we can prove a fairly good bound for sunflowers in set systems with bounded VC dimension. So this originally here in my thesis, but then officially in the paper, it appears in joint paper with Bernstein. Therefore, we show that if H, the family of L sets, VC dimension at most D, and I'll define VC dimension in 1 second. And the size of H is at least some constant times R times log D plus log star L to the L, then H has a sunflower. So here we say that H has VC dimension at most D if there does not exist any D+1 size set S, so that for every subset T of S, there exists some H from our family that intersect S in exactly that subset T. Okay, so no set S of size D+1 is shattered. And again, in order to get bounds for sunflower, we only need to work in the corresponding spread, not small context. So actually, as you are by now familiar with this, the main step would be to prove the following. So if H is L-bounded, not D small, and VC dimension at most D, then a random subset of X with density CP log star L log B will contain one set from H with high probability. So this is the version of improvement for the Kahn-Kalai conjecture, improvement to the log factor if you have about this VC dimension property. So again, just to showcase the idea, the proof will be fairly similar to what we always do. So, okay. But we do need to be a tiny bit more careful with the cover that we use this time. So let me set it a bit more carefully. So for set W in X, let's recall the usual family of heavy fragments that we consider. So this will be just the family of all fragments TWH, where H is some set from the family H, and the size of T is too large. For us, before, too large means larger than a half fraction of the uniformity L. It turns out that under bounded VC dimension, too large we can push down on the way to roughly some constant times D times log. So this is why you get the log star. Okay, but this turns out to be not actually the correct family we use for the cover. What we would use for the cover is actually the following collection. Let me denote it U bar W. So this is the collection of all sets of the form H intersected with H hat of Z, where, well, Z is the union of W and T of WH. So really, I'm digging into the proof and pick out what should work for the cover, and that will work. So, okay, also one additional mention. The fragment T is at least CD log. Okay, so of course, this is still the cover for every set H, which does not give rise to a small fragment by definition, right? It's a subset of H. And every H that does not produce a small fragment is going to be covered by this family U bar W. So as before, our goal would be to control the expected P cost of this collection U bar W. We want this to be small. So, okay, let's do the rewrite as usual. You can write this as sum over W, PCP of W. Sum over H, where T of WH is large. as usual, we know how W can be identified once we start from Z. So again, we change the variable. We switch the sum from W to the sum in Z. And then that's the usual change of measure factor. Okay, what's inside? Let's be a bit more careful now. So what is happening is we have this sum up here over W and H, right? And now we start from the set Z. Well, from Z, we know that, so from Z we have for free this set H hat of Z. We know that H hat of Z will contain the minimum fragment T. Okay. But furthermore, what we care about is actually this intersection of H and H hat of Z. Let's be a little bit careful. Let's be careful. So again, for the same sort of reason, if you're just working under the not P-small condition, you have to be a bit careful. So here, I'm going to sum not exactly over H, but I'm going to sum over all of the sets U that can be written in the form H intersected with H hat Z, or some H from the family script H, where the fragment T of WH is large. And here's just P to the side of P. So the sum have to be in U, not in H. That's a somewhat more important point. Okay, so this stripe set is our set U. Well, what do we know? U always contains T, right? So U will have size at least T. In other words, I can write here the summation in this way. Once I fix Z, I know what is the set H hat of Z. So I'm summing here. In Z, all of the sets U that can be written in the form H intersected with H of Z with size at least T. And I have P to the U. Every U that can be written in this form of size at least T. Why did we do that? Well, we have the condition that the family H has VC dimension at most T. So you can actually deduce that the family of sets of the form H intersected with this fixed set H hat Z. This also has bounded VC dimension. And now, because it has bounded VC dimension by Sauer-Scheller, but also Vaples-Chervonenkis, you have an upper bound, right? The number of sets of the form H intersected with H hat Z, where H comes from our family script H. This is actually at most something like L to the D. So something like L to the D, maybe E L over D to the D. It's a safe upper bound. So the standard result of our set system with bounded VC dimension. And here L is just coming from the size of the set H hat Z. Okay, so that is quite good input.
As in the smooth case, we are really fighting for locating this T. In this case, we have VC dimension helping us
Right.
limit the choice.
That's right. Exactly. So VC dimension limits potential choices for how two sets image can intersect, which is how we can, why we define U bar this way and why it helps. So if we use that bound, then we can continue the calculation. We can sum over large T, and we have the familiar factors. In the final factor, we can plug in that bound right there. So EL over D to the D. And when we have the sum of P to the U, where U is at least the size of T. So anyway, that is going to be at most P to the T. So we have this bound. Okay, so now you can see why we picked CD log L, right? So the only thing, the main thing we need to fight here is this factor of L to the D, so E to the D log L. And we have this factor of C to the minus T fighting against it. So if we choose T to be a constant times D log L, we can guarantee that this is very small. Something like L to the minus some constant. Okay, so this is essentially the proof. Right, so we use the same thing again. We do the iteration, just as in the proof of the Kahn-Kalai conjecture, or if you prefer, you can do the easier version where you run it in a spread setup. And what this is producing is it allows your fragment to shrink by a log factor in every step. So roughly after log star of L many steps, you are done. Okay. So right, so that was a few applications among this world of sunflowers or assess systems, and this will, yeah, so the smooth spread property in particular will be fairly useful for us in the last 2 days. And one of the points here was really, as you see in the proof, we always do the same thing. So once you are familiar with the proof of the Kahn-Kalai conjecture via the minimum fragment that we saw, and in particular, just this one non-trivial step where we do this change of probability measure between W and Z, then all of these applications will fall in a very streamlined fashion. So, well, maybe for the last few minutes, we can take a break at this point anyway. I'll mention briefly the last application, which is of a different nature. So it's an application of this short version of the selector process conjecture that I mentioned, which is a somewhat of a more abstract statement. So again, the theorem statement there. You have H, which is not P small. And then some adversary can come in and then give you all of these weights or coefficient vectors, whatever. You have the condition that the sum of the weight is at least 1, let's say equal to 1. And then the conclusion is that with reasonable probability, if you sample a random subset with density Cp log 1 over epsilon, then you sum up the weights inside some set H from your family, you get at least a 1 minus epsilon fraction of the weight. Okay. So what is the application I want to tell you about? Again, this is regarding conjecture of Talagrand. So in defining and imposing the fractional expectation threshold, he conjectures actually that the fractional expectation threshold is always equivalent up to some constant to the expectation threshold, which is by itself fairly magical statement because this expectation threshold and fractional expectation threshold are very general, define very general context. And in general, it's the relation between a linear program and it's an integer linear program and its relaxation. And Talagrand's conjecture somehow suggests that for this vast family of linear programs, there is always this, essentially this only this small gap between the integer problem and the relaxation. It's fairly surprising. And again, somehow, Talagrand has an extremely rich and wonderfully broad picture regarding all of the intricate phenomena here. So we still don't know a full resolution of Talagrand's conjecture. And before we know quite limited cases of the question, but now let me tell you one of the corollary that you can prove with it. So really the statement you can equivalently state as the statement that if H admits a fractional cover W that is small in the sense that the sum over W of P to the side of G is at most 1/2. Then you can also construct an integral cover but now with the sum of P dividing by some constant potentially raised to the G at most 1. So it's something about being able to round a fractional cover to an integral cover. And what we know is now is that if H has a fractional cover W with small count, and W is supported on sets of psi at most T, then H has an integral cover that is P over log T. So we can round fractional covers to integral covers, but in this rounding procedure, we do lose this log T factor in the uniformity of the fractional cover. We do know though that if the fractional cover has quite large uniformity, like log N, then result Fisher and Person shows that we can round the fractional cover quite efficiently. So this at least is speaking quite well about the complementary range, even though this log T factor doesn't allow us to completely resolve the conjecture of Talagrand. And okay, don't think I will have time to tell you about the full proof. So I'll just tell you that the proof idea is actually fairly simple. So what you do is you assume that H is not Cp over log T small. Well, I want to use the sharp version of the selector process conjecture, so I need to set up some weight. But there's a fairly natural notion of weight that you can use here. So for instance, you can just take the weight lambda H of an element X in H to be, well, the sum over all of the sets W fitting inside H that contains this element X. The weight, fractional weight of W in the fractional cover. The right way is to do this. And then normalize it. Okay. And once you take the conclusion of the sharp selector process conjecture over there regarding to this weight, then you can deduce a contradiction against the statement that W is a small fractional cover. Okay. Now, there are about 2 minutes, so I think I will unlikely be able to tell you a lot about some of the ideas behind how one can prove either the original version of the selector process conjecture or this short version of the selector process conjecture. Actually, I should also mention that there is also a later paper by Bednorth, Martinek, and Miller, where they give some simplifications to the original proof of the selector process conjecture, and they extended more in the probabilistic context to other classes of stochastic processing. Now, at least maybe just a single word about how you may at least start proving these results. The proof in a very high level will be still fairly similar to how we prove the Kahn-Kalai conjecture. Actually, that's how the Kahn-Kalai conjecture is almost a subset of that proof. You do it appropriately. What you need to change in your perspective is to think about redefining the minimum fragment in a somewhat different way. So originally, when we define the minimum fragment, which has a very simple definition, turns out in this context, the better set to start with the definition is not the minimum fragment, but the set Z and the notion of feasibility for Z. So for example, for the selector process conjecture, it turns out that the right notion to use is to say that a set Z is feasible if there exists, okay, some H from the family H and set W in Z such that the following property holds. So, okay, now this is a bit definitely too short of a time to tell you what happens here. So what you need to do is to, well, first, for every H from the family script H, let's order the elements of H according to decreasing order in the weight. So let's order them so that lambda H of H1 increase lambda H of H2 all the way until the last element. I'll define a special index for every W. We can define a special index B of WH. So this should be the smallest index so that we can still guarantee that W captures a large fraction of the weights in the tail segment. So such that the sum over J bigger than B of lambda H of Hj, indicator Hj is in W. This is still at least a constant fraction of the sum over all of these lambda Hj. Okay, so somehow for the tail, we can guarantee that W catches at least a good fraction of them. And because W already quite successfully captures the weight of the tail segment of the set H, what we want the set Z to capture is not that tail segment, but just the original segment. So such that Z contains H1 up to HBWH. So this turns out to be the right definition for feasible H, and then your minimum fragment T is the usual way. So this is the minimum subset of H such that W union T is feasible. And then one can trace through carefully in order to do the same key property encoding swap the order of the summation in order to prove the original version of the selector process conjecture. And for the sharp version, it's going to be even more complicated. So the notion of the main thing that one needs to write down and understand is just the notion of feasibility. And in the end, what we will have now is not the minimum fragment, but what I call in the end the tower of minimum fragments. So if you are interested, you can take a closer look in the paper. That's all. I'll take some questions.
So these things for the sunflowers, they actually wouldn't work if we would want to have a sunflower that has a non-trivial center.
So Well, already, well, the original pre-processing step, I guess, already put something into the center. Right, there's this simple greedy procedure at the beginning where we put things into the center.
But couldn't it happen that you sort of directly jump to?
Yeah, but it could happen that originally at the beginning you are already spread, and then anyway, there's no guarantee that you would have a sunflower with a non-trivial center. For example, all of the sets could be disjoint, right?
But is there are there some bounds? Is there some conjecture? Or I guess then it would also depend on the size of the set.
Yeah, then that may depend on the crowd set or some additional condition that you put on the set system. So I'm not sure if there's one that guarantees the notion of set.
The like the bond in like after sorry, I'm talking about some power problem. Is the bond after like pre-processing, like assuming the spreadness is that bond not height, like is it also contributes CR to the out.
Oh, so you are asking.
So I'm just asking if I want to find like disjoint sets and assuming the spreadness.
So no, so we only know that the bound is tight if the only way that you want to find a disjoint set is by random sampling. Is to do this trick of random partitioning and random sampling and try to find a set in there. That's where we know that that bound is tight. But if you are allowed to carefully search, then we don't know if that's tight. Maybe it's still constant to the end. And right, in fact, there's some conjecture of Talagrand which may suggest that it should be true that once you go beyond random sampling, you may just need this constant 2DL in order to get the disjoint cells. It's essentially.
So there is some questions in the chat. One question is, in the application of sunflowers, brightness looks like pseudo-randomness for set system. So can we find some similar forms of spreadness for set systems on the flip, or maybe some abelian groups? Some form of spreadness for abelian group, something related to.
Yeah, so actually some formal notion of spreadness in abelian group. So yes, and so the same spreadness property. So indeed, it's a correct observation. The spreadness is a form of a pseudo-random kind of property. It actually also appears maybe under some different name in the study of hypercontractivity and the various different types of domains. So they already might find some different generalizations of it, but also kind of the same spreadness property appears in works around sets avoiding three-term arithmetic progression. So the breakthrough by Kelly and Maker and a lot of the follow-up works. And there, indeed, it's a form of spreadness in an abelian group. So spreadness takes the form of you cannot pass to a subspace or subgroup of reasonably small codimension defined appropriately, and after which the density of the set jumps up by a lot. And that property there is kind of the key property in their work, as well as some other work on hypercontractivity, as well as.
There is another question which is in the middle of around 10:30. I missed it. Sun Tong was asking, you still have to show that the families produced after each iteration is still p-spread, right?
Right. Yes,
This
but
is which question?
I guess it may be after when I state the key lemma and the p-spread, then after one iteration, you can show that almost all sets produce a small fragment, and then I just take the small fragments to be my next family. These still have to be p-spread, but because they are almost all of the original set, they almost just trivially inherit the p-spread property from the original family. There's a little bit in the loss in the parameter, but one can be just careful and these don't affect much.
Maybe one more question. From Veronica asking, I was wondering for the definition of the expectation threshold, since for the graph version, this is the expecting number of subgraphs H in GNP goes from being less than 1 to growing to infinity. Why this time we consider 1/2? Could the definition also has worked if we had a one there, or am I confusing something in the definition?
Right, so I can maybe vaguely ask, I guess, what the question is about. So, yeah, and maybe to compare to the coerced notion of threshold, this is a fairly specific threshold, and everything is chosen around 1/2. For the expectation threshold, you cannot change really 1/2. You can change 1/2 to almost any reasonable parameter, but perhaps not one, just because at one there is a special cover that works for every set system, and that's just the empty set. And so if you want to find the cover with cost one, then it always exists, and that's kind of what we want to avoid. If you now ban the empty set from the cover, then there would be some interesting stories, but yeah, so it gets interesting, and it actually appears in some of the recent works connecting these type of phenomenon to hypergraph containers, but might be too long a digression at this point.
So maybe let's thank Huy for the lecture.